Okay, can everybody see my slides? Or
Yes.
just one person? Yeah, okay, yes, fantastic control question. So that got established. All right, so again, thank you very much for the introduction and thank you for inviting me to do the keynote. And of course, the introduction clarified that I'm a senior computer scientist and lead the Chameleon project, about which I'm going to talk to today. But if you kind of asked me, what do I do for a living? I would generally say that I build scientific instruments. And those scientific instruments are rendered in infrastructure or in software, depending on the context. So if we think about a scientific instrument, generally speaking, if I can advance this, generally speaking, we think of something like this, right? So, for example, biologists use microscopes, astronomers use telescopes. Some scientific instruments are very, very large, right? So CERN, the Large Hadron Collider at CERN, famously so large that no single country could afford it. What is the scientific instrument for computer science research, right? What do computer scientists need? And to answer that question, we have to consider what type of research computer science engages in, right? So our users in Chameleon, of course, is an instrument for computer science research. They develop new operating systems or they think up new virtualization solutions, new networking protocols. So they do level sometimes on system science, sometimes at the very low levels of the software stack, right? And for that, they need hardware that is deeply reconfigurable. We can boot from custom kernel because you're developing one, and you also have, for example, serial console access in order to debug that custom kernel. They need an instrument that provides a wide variety of hardware and cutting edge hardware, right? Very important that it's diverse and that it's cutting edge, because we want to explore the phenomena that nobody has explored yet. And we want to look at software and how it evolves on those newest architectures, not the architectures that we had 10 years ago. And this is also a very important aspect of every scientific instrument, is that it needs to evolve. And why? Because the science evolves constantly, right? So science evolves, and in order to explore it, we have to evolve the instruments we have, right? So the telescope arrays of today, for example, they are not the same telescope as the one designed several centuries ago, right? And similarly with microscopes, they're also very different. So an instrument is constantly evolving. And so today I'm going to talk to you about an example of such evolution. So when Chameleon, a testbed for systems research again, was first conceived, people were thinking about cloud computing as the emergent research areas, and maybe networking. But of course, in the last decade, we saw the emergence of IoT devices and edge devices that work with those IoT devices, or that might provide the processing backbone for those IoT devices. And this is a very powerful development, because those edge devices tend to be very inexpensive. They tend to be very nimble, and it's possible to deploy them in all sorts of environments, right? So it's possible to deploy them in our cities as part of wearable technologies or as part of instrumentation of various city services. It's possible to deploy it in our fields and rivers and forests, and have it bear on precision agriculture and so forth, in rivers, in the air. And we can deploy them and ultimately instrument the planet and understand better questions in environmental sciences, questions in quick response to disasters, and we can investigate various other phenomena that were completely out of reach before. But in building this scientific instrument that spans the globe, we have made the first step, right? There has been the breakthrough that developed the Internet of Things and edge devices. But in order to really build this instrument, we have to explore issues of scale, of connectivity with those devices, right? Which is often very intermittent. security, very important, interactive dynamicity, resilience, data management. These things are going to be producing huge amounts of data, and so on and so forth, right? So many other research questions that are cutting edge right now, and they're the great unknown right now. And of course, I can't tell you, and I'm not going to tell you what the solutions to all these problems are today, but I am going to tell you about the scientific instrument and how it evolved to help you as a community answer these questions. So first, just a few main points about Chameleon. What is Chameleon? So chameleons, of course, as everybody knows, like to change. And as we already talked, an instrument for computer science systems research has to support deep reconfigurability, right? So it has to be possible to power it on or turn it off, reboot it, boot from custom kernel, have access to your console, all those good things. And at bare metal level, because if you're working on something like performance variability, for example, or power management, you really want to have very direct access to the hardware. Now, that can be sometimes expensive, right? The nodes that we're buying now for Chameleon, they have more than 100 cores per node, right? 128 nodes per node for the AMD nodes that we're buying right now. So in addition to this bare metal reconfigurable infrastructure, we also have a KVM cloud. Right? And KVM cloud allows you to slice to deploy virtual machines, right? And slice the node and make it available to multiple different projects, uses the resources more efficiently for projects that can run in virtual machines, right? It's possible to do systems research in virtual machines. It's just that there is a large set of research that cannot be done in virtual machines. In terms of hardware investment, we seek to balance support for large scale versus diverse hardware, right? So our first investment in hardware yielded about a homogeneous partition of about 15,000 cores to support experiments in big compute. We've got over 6 petabytes of storage right now, which is distributed over the nodes in various interesting ways, but we also have a 3.5 petabytes global store for storing data for experiments that deal with big data. And initially, all of this was distributed over University of Chicago. Right? I'm the PI of Chameleon. I'm also the PI of the University of Chicago site and the Texas Advanced Computing Center, TAC, right, which is also a partner on Chameleon. And those two sites, they are large supercomputing centers. TAC, of course, is the home of Frontera. Our hardware at University of Chicago is actually in the Argonne Leadership Computing Facility machine room. So both are large supercomputing centers, and they're connected by 100G network. So you can also push scale by experimenting with large networking flows. But we also have an investment in diversity, right? So we've got ARMs and Atoms, we've got FPGAs, we've got various different generations of GPUs, support Corsa switches as well, and so on and so forth. Now, we also packaged the Chameleon infrastructure. CHI stands for Chameleon Infrastructure. So in other words, we put it in a box and the package, the infrastructure and the operations model. And now it's possible for other sites to deploy it, right? To deploy it relatively easily and manage it relatively easily. And our colleagues at Northwestern took us up on this, and they deployed a Chameleon site. So now we have 3 sites. And we are now working also with colleagues at NCAR. And that site will hopefully come online soon and will be used in the student cluster competition at this supercomputing. So if you're interested in the student cluster competition at supercomputing or go to supercomputing in general, that's a good thing to check out. And at IIT, at UIC, and we're talking to also to several other places for deployment, right? So when that is accomplished, Chameleon will become a much more distributed testbed. One thing that is very interesting about Chameleon is that unlike many bare metal reconfigurable systems, Chameleon was built on top of a mainstream OpenStack technology, open source technology called OpenStack, right? And while most of you may be familiar with OpenStack as managing something and managing virtual machines, it also has a component called Ironic, which allows you to manage resources on bare metal level. That's what we're using. And of course, this has many advantages because OpenStack is familiar to both users and operators. If it's not familiar, they learn about it, they acquire transferable skills. We leverage contributions, open source contributions of community that numbers in the thousands. And we were able to also contribute to that community. And we contributed in particular component called Blazor, which does advanced reservations, and that is now recognized as official OpenStack component, right? And being also mainstream infrastructure has the advantage that there are many commercial tools that, for example, convert images from OpenStack format to something like Amazon. OpenStack works with CloudFormation, for example, also. So there are many, many connections to other parts of the computing ecosystem. And then finally, a testbed, a good testbed provides not only resources, but also allows users to use those resources more easily. And so we invested in reproducibility, repeatability, and sharing for supporting those things, and provide Jupyter integration. We provide access via something called Chameleon Daypass that I will describe later in more detail. And we've got something called Trovi for sharing experiments and allow you to publish also your experiments to Zenodo, right? So I will describe all of that in the later part of the talk. Okay, so Chameleon in the numbers, we have served over 6,000 users who worked on 750 projects and produced over 400 papers. And Chameleon has been in existence for over 6 years now and has 3 more years to grow. A quick look at the Chameleon hardware quick map. So we started with 12 racks of Haswell processors, like I said, 2 sides connected by a 100G network. And in phase 2, we added 2 racks of Skylake processors at University of Chicago. So that was a nice upgrade. At TAC, we added Skylakes and Cascade Lakes. And we are hoping to release 3 more racks of Cascade Lakes and all sorts of interesting hardware at University of Chicago this month, right? So watch for an announcement. It's coming soon. Each site has a sizable storage system, 0.5 petabyte at University of Chicago, 3.5 at TAC. And in addition, TAC has also a bunch of heterogeneous systems. At University of Chicago, we also have now heterogeneous systems, especially GPUs. And then, of course, Chameleon is federated to Fabric, to the different associate sites that I just described, and to infrastructure called CloudBank, which is an NSF-funded project that supports access to commercial clouds. So we actually we published a paper recently called Overcast that provides a recipe for connecting for constructing experiments over Chameleon and commercial clouds as well. So this is just a summary of what was on the previous slide. To that, I will just add that by the end of this month at University of Chicago, we're hoping to release 3 new racks, which, like I said, will have Cascade Lake nodes, will have GPUs, FPGAs, will have a variety of different SSDs, will have new InfiniBand fabric. So those GPUs will be connected to the InfiniBand, will have nodes with Optane and those SSDs. So you will be able to experiment with disaggregated hardware using this InfiniBand fabric as RDMA between nodes with very rich storage and GPUs and other interesting devices. And then, of course, we also added IoT devices, and more about that later. All right, so that was the hardware. Now, how is this hardware configured? So if you think about your typical experimental workflow where you formulate a hypothesis, then discover resources, right? If you're working on machine learning, you want something with GPUs, probably allocate those resources in order to gain temporary ownership of those resources so they are just for you and not anybody else. And then you reconfigure them, and then you finally run your experiment and monitor it. So here is a sort of overview of what we provide for each stages of that experimental workflow, right? So for discovering resources, we have very fine-grained descriptions of our resources, and it's automated. So it's always up to date, and we version it. So whenever we change something on the system, we upgrade memory or change disks or something like that, we version that. because your experiment may return slightly different results because it's running on a different hardware, and you need to know that, right? So we're trying to make it as close to the situation when you have the resource in your lab as possible. Then you can allocate resources, which you can do on demand if they are available. But if you want to, you can allocate them via advanced reservations. This is very useful, especially if you want to experiment with our GPUs, right? They're very much in demand. Everybody's doing machine learning these days. Sometimes you come to the test, but they're all taken, right? So then being able to make advanced reservations for when they are available is very, very handy. This is all, like I said, deeply reconfigurable. We give you a catalog of commonly used appliances that, for example, support things like TensorFlow, so they are sensitive to the hardware we have. You can take those appliances, you can configure them further to reflect the environment for your experiments, and then you can snapshot them, which means you can save it, right? You can save this configuration, so next time when you come to the test bed, you can start from that saved appliance, right? You don't have to redo that reconfiguration step yourself. We support orchestration. So that means if you want to automatically deploy something like a virtual cluster or a cloud configuration, it's very good for that. We're integrated with Jupyter. That's another way of doing orchestration. And we also support networking experiments via stitching and software-defined networking experiments via something called Bring Your Own Controller, right? And all these, and we also provide fairly standard monitoring capabilities. All of this is available via 3 interfaces, via a GUI. We have a command line interface as well. And we have an interface, we have a Python library that you can also program the testbed with. And in particular, most of our users use it via Jupyter. Access via federated identity, that means that you don't need Chameleon account. You can log in with the account of your institution. You can also log in with your Google account. That's very popular for students. So it's relatively easy to use. Okay, and so now just a quick, last but not least, we've got a paper where we describe how the various design decisions that we took on Chameleon, how they enhance the testbed. So if you're interested in learning more about the capabilities or why they're there, I highly recommend this paper. A few vignettes of various different projects that our users ran over the years. So here's one from a student at University of Pittsburgh. She was looking at performance between and examining performance difference between HPC applications running under virtualization and under containerization, right? And for that, she needed this bare metal configuration. She needed to boot from custom kernels. She was fine-tuning different kernels to provide an apples-to-apples comparison, ability to save her work, right? So you do all this hard configuration work, you want to save it, support for large-scale experiments, and up-to-date hardware. Another one, here's an example from my colleague at Argonne, Swan Perano. He was working on developing exascale operating systems and had very similar requirements as you on the previous slide. He needed to boot from custom kernel. He needed up-to-date hardware. And he needed a whole disk image boot because he was using kind of a parameter search over different kernel parameters. Another completely different project now, a project on security and classifying cybersecurity attacks from a group from University of Arkansas at Pine Bluff, so a very small university. And they were actually using our KVM cloud. So this is a good example of a project that doesn't necessarily need bare metal reconfiguration, but they needed pre-configured images, which of course we provide, and access to the infrastructure from multiple collaborators on different sites. Another project is from the area of networking. This is a project that was building software-defined exchanges, and for doing that, they needed to be able to create dynamic VLANs on Chameleon and use stitching to combine them into wide area circuits. And then they also needed orchestration, so managing complex deployments. So the project diagram that you see here shows that was a very distributed, those were 4 networking enclave in 4 different areas. So standing up something like this can be time consuming. And if you can automate that process, that's a big win. Another project on data science research from a couple of students who are working on Chameleon. Those are undergrads who made it to the semi-finalist stage of the ACM student research competition at Supercomputing 17, as you see. So, a few years ago, one of them was working on image extraction, and the other one was working on managing storage, and they needed access to state-of-the-art GPUs, storage in various configurations, and then also orchestration appliances, so things that allow you to automate your experimentation. And then a very exciting project from a student at the University of Massachusetts at Amherst. She was working on adaptive bitrate video streaming. And as you can see from the diagram there, she was creating those really complex networking configurations, right? So you've got multiple switches there, multiple nodes, 2 network circuits, one was slow, one was fast, and she was comparing how her streaming algorithms were going over those connections. And her experiment is very interesting also from the perspective of how she did what she did, right? So what she did was very exciting, but how she did it, she was our first Jupyter user, right? So the first user who packaged her experiment in a non-transactional way available for reproducing. Power capping, an experiment from a University of Chicago student who was a finalist for the Supercomputing 19, the student paper. And last but not least, and I just put a few examples of user research on one slide, because these days we have a blog, and every month we interview one of our users, right? And they tell us about their project. So all these 3 experiments here you can find on our blog. You can find out more about them. But the point I'm trying to make here is that increasingly our users started looking at edge technologies and IoT. So for example, you see here this project on biometrics that was essentially exploring how to train models that can recognize the difference between a human face and the mask of that human face, right? So if you can think of your iPhone and it's reading your facial features, how can it tell if it's you or somebody made a plastic mask, right? Or a fingerprint spoof or something like that. And of course, to do research like that, you're dealing with a lot of personal data, and that data, is often not available. But you can train models using something called Federated Learning. And so we also hosted research from another group, a completely different group, on Federated Learning, right? So Federated Learning trains those distributed models and then has an aggregate that aggregates them into one model, right? So you can't move the data, but you can train those models in situ and then aggregate them. And that typically comes up in IoT or edge scenarios, which those edge devices, typically those federated models are trained on NVIDIA Nanos or some other GPU-enabled edge devices. And then last but not least, network traffic fingerprinting for IoT devices, right? So you can network traffic fingerprinting is you look at the network traffic, and from the network traffic, you can infer of what's going on in the environment, right? So you can, for example, have somebody who has a refrigerator. Those things are very smart. And from the network, you can tell whether the refrigerator was opened or closed, right? So you can tell what's happening in a room based on that network traffic fingerprinting. Of course, you can tell other things, right? You can reason about various security properties of networking and things like that, right? But this is very often also done in the context of IoT Edge, and that project was specifically addressing IoT, right? So those were projects that were done on Chameleon before we decided to add an edge test to the system, right? So users were using Chameleon as a platform for simulation or for emulating the phenomena that they were interested in, right? But of course, emulation can only take you so far, right? You can't, for example, reason very well about what the power management properties of your algorithm are, right? For something like this, you need an actual experimental deployment. And so out of that arose this desire to have an edge test bed added to Chameleon that will provide a realistic edge to cloud experiments, and our users also said from one Jupyter notebook, right? Because everybody loves Jupyter notebooks. Our users started using them very extensively, and that's their way of saying we want that through one interface. So what does an edge testbed look like, and how do we design one, right? So some of our users said, give us something exactly like Chameleon, only on edge, right? But others said, well, wait a second, an edge testbed is not like a cloud at all, right? So first of all, when you have a cloud, you have a bunch of resources in a data center. Now, the point of those edge devices and the IoT devices is they are out there in the wild, right? They're not in data center. They are sitting somewhere in a forest, right, looking for forest fires, or they are wearable technology that sits on people's clothes, or you know, they are your little IoT devices, your watches and your phones and things like that, right? So have to account for that somehow. Furthermore, the edge devices matter, but it also matters what's attached to them, right? They are attached to cameras, they are attached to actuators, right? They are attached to software-defined radios. And many of them are not server class, right? So something like IPMI, the thing that allows you to do bare metal reconfiguration, doesn't work for them. Right, so out of that arose this concept of the testbed, where we do reconfiguration via container deployment, right? That gets around the fact that bare metal reconfiguration is now hard, has support for peripherals based on an extensible plugin model, because we can't support every peripheral in the universe, right? So ultimately, our users will have to support them. And most importantly, relies on mixed ownership. Right, so it's no longer the case. I mean, we provide some edge devices in the data center. The user said, well, we want to add our own edge devices. We want to add our own edge devices and have them connect to the cloud in order to do the experiments. But some of those edge devices, it doesn't make sense to share them with everyone. I'll show you later. One of the projects running on our testbed is a project that somebody teaching a class on autonomous vehicles, right? So a class on autonomous vehicles, it doesn't make sense if somebody, just a random person, comes and allocates the Raspberry Pi that is connected to an autonomous vehicle, right? Because they don't know where that vehicle is, what to do with that vehicle. It just doesn't make sense. So anyhow, this was the rough shape of the testbed, and we said for last summer, let's see what our users can do with that. Let's have a little workshop at the end of the summer, share experiences. And of course, the workshop is already in the past. It was in September. But if you go to this URL here, you can watch the videos from the workshop, and you can listen to the user presentations, and also to our presentation and demo of that edge testbed, if you're interested. So another thing that we wanted to do with the edge testbed is use it as a platform for additive innovation, right? So provide this layer that can be sitting on both Chameleon-owned devices and various user-owned devices, but that also gives you something that you can put your own research on, right? So there's many people exploring and doing fantastic research in exploring power management and edge security and edge to cloud workflows and various ways of programming those devices. What we aim to do is give you the base layer, and then on top of that, you can package that with the research that you're doing and give your users, or perhaps you can give your users a stable platform. And just to give you a little bit of eye candy, for example, we moved from the data center to little edge devices. This is roughly what they look like. What does that now do, this edge testbed, to this experimental workflow that you saw below? So first of all, the discovery right now is very bare bones. So we've got a web page, and it lists the various devices that are available via our data center. So those are edge devices that sit in the data center. In terms of allocating resources, you can do everything that you could ever do with bare metal resources with Chameleon, right? So you can do advanced reservations, you can do on-demand you can say, give me a Raspberry Pi, and then the system will assign whatever Raspberry Pi is available. Or you can say, I want that specific Raspberry Pi, because you know that that specific Raspberry Pi is attached to a self-driving car that you want to work with, right? So then in terms of reconfiguration, like I said, we do reconfiguration by containers. We, again, provide catalog of images. You can snapshot those images, so you can configure them and create a new image. And we provide that coveted Jupyter orchestration, Jupyter integration for orchestration. And in terms of interfaces, we again provide everything that we ever provided, meaning a GUI, a command line interface, and interface via Python. And you can log in via a federated identity, right? So if you want to experiment with the testbed today, you can log in. You're gonna have to have a project. So maybe somebody can add you to a project, or you can apply for a project, and you can use these interfaces that I described here. Sharing devices through SDK, like I said, very important for our users. They want to add their own devices to the testbed, but they want to add them for restricted sharing, right? So that's a very important feature. For example, they are organizing class, self-driving cars, or other things, right? Or maybe they have a collaboration that deals with specific things, wildfires, looking at various demographic issues in the population, right? Looking at social distancing during COVID. They want those devices to be available to their collaborators only. So that we also support. And then, of course, they want to have those devices have access to camera modules, software-defined radios, other things that they need. So here's a few vignettes now of the projects on the edge, right, in the edge area. So the first one it's the self-driving car class that I was talking about. It's organized by Rick Anderson, who's the director of virtual worlds at Rutgers University. And he's been teaching now for a while classes based on self-driving cars. It's a great way to introduce young kids to the concept of machine learning. So those cars, you've got a picture there of a car. Each of those cars is associated with an edge device, so with something like Raspberry Pi or NVIDIA Nano. And the cars drive around the track that you see on the bottom there. They use the camera to get the data about the track, and then they learn. There's a steering module, an actuator in the car. So based on they see, it steers the car, right? So that's what it does. And but it turns out that organizing the class is actually a very logistically complicated process, right? So understanding which Raspberry Pi is on which car and how they connect to the network and so on and so forth was difficult. What he did is he added those edge devices associated with the cars via the SDK to our edge testbed for restricted sharing with his users. And now our testbed provides the login for those users, provides the management of those users. It gives them interface via Jupyter. Again, a big selling point with many people, gives them a consistent network connection, and also gives them a connection to the cloud, right? So the cars drive around the track, they produce a lot of data. It's convenient to now send the data to the cloud and use it there, train it there, or archive it there. So here's a quick look at what these self-driving cars might look like when they grow up, right? So self-driving cars, this was a class, this was a great exercise for kids, but self-driving cars and self-driving vehicles in general are very important in precision agriculture, for example. So on the bottom here, you see an agricultural robot. It's a phenotyping robot. So it's equipped with many cameras, and those cameras, this robot drives around the field, and those cameras look at corn stalks, or we look at what the what the plants look like, and based on that observation, reason about what those plants still need, right? They need water, they need fertilizer, or other things like that. So this is a set of challenges that is addressed by a project, a recently funded project called ARA. And that project is essentially a wireless testbed, but a wireless testbed that has this incredibly hard task to bring inexpensive wireless to rural and to rural communities. And of course, you need wireless to operate all those different devices. Once that happens, it becomes possible to orchestrate advances in precision agriculture, orchestrate advances in land management and other issues. And they are using Keynote for managing those devices. So actually they asked for something like Keynote in a box. They're going to create a separate edge testbed. For now, they're experimenting with our testbed. And they are also going to collaborate with us on spectrum reservations, wireless spectrum reservations. So just like right now in Chameleon, you can make reservations for nodes or edge devices, right? You could reserve a wireless spectrum band via those same means. Yet another project, this one in the water now. This is a group, it's a project in marine biology. And those are biologists seeking to map existing fish populations, right? And understand better how various environmental factors impact their habitat, right? So they have these floats that you see in the bottom of the slide there. They're equipped again with edge devices. Those edge devices can now be added to Chameleon, right? But those edge devices can also float around on those vehicles and look at fish. The vehicles are also self-driving. That's another system though. Look at fish, recognize fish, and follow fish around. So as the situation changes, that can impact how the vehicle drives around, right? So. Last example to cover land, water, and air is a project called Flynet. And what they do is, well, they look at various tools that support edge computing devices in scientific workflows. But what they are trying to do is essentially develop flight control for various drones. So the picture on the bottom that you see there is, you see a weather moving, and there are two kind of purple, hot pink kind of lines of point A and point B for various drones, right? And what the flight path might be. And of course, you don't want to fly the drone through severe levels, so it's not a straight line, right? But now, as the weather moves, you can update that flight path of the drone with the moving weather. So what they use Keynote Edge for is, for edge computing experiments. They are also using our various reproducibility vehicles, and they are also seeking to provide tools for other researchers to include Keynote Edge in their workflows, right? And that last thing is a very important point, because edge computing is a new area, is an evolving area. And for example, what happened at the workshop that I just told you about, a workshop of our users, where they were exchanging experiences, is that many people, they were listening to somebody's presentation saying, gosh, that's fantastic evaluation. Can I get your code? I would just like to run it on my own edge device and see how that behaves, right? So there is a lot of demand for something that others created. And the biologists from the last slide, they are biologists. They're not necessarily experts in edge or computer science. They would love to have a machine learning module that they can just plug in and go with that, right? And focus on their science. So this sharing aspect, because this is an emergent area, is becoming very, very important. So the last bit of our talk is, what we're trying to do is bolster that sharing aspect, right? And make it easier for our users to reuse each other's codes and rerun each other's experiments. And in particular, you can think about it as a goal. Can we share experiments as easily, right, as we share papers today? Right? When I enter a new research area today, I go and I do literature search, and I read a bunch of papers, and I try to find out what others have done in that area, right? But I don't rerun their experiments, largely because very often there aren't experimental artifacts that I can rerun. But even if they were, it's sometimes very, very difficult to do, right? What I would like to do is kind of like what you see in that picture, is I'm reading a paper, I see an interesting graph, I'd like to click on that graph, and I would like that to take me to a place where I can experiment with that graph. So maybe I want to see an average of those values, right? Or maybe I want to see more values or whatever, or even rerun that experiment, right? So this is something that we seek to do. And that paper in this picture, in fact, you can do that with that paper, because this is a paper where the paper itself is the result, right? And let me tell you about that. But first, let me tell you testbeds and public resources, what I call instruments held in common, are extremely important to reproducibility, right? Because if there is a testbed, that means a public resource, that means that it's no longer the case that I can experiment with machine learning because I have a GPU cluster in the basement of my department, and you can't because you don't have access to those GPUs, right? With a testbed, a public resource, everybody has access to those GPUs, right? So not only does it democratize hardware, but also creates a baseline for reproducibility, right? Because you can allocate those GPUs, not just that you can get the specific GPU that I was running on, right? So you definitely can get access to that hardware. And of course, like I mentioned earlier, that hardware is versioned. Secondly, if you use clouds for sharing, you are essentially more than halfway towards creating a reproducible artifact, because the situation is very different than when I'm running something on my laptop or when I'm running something in a lab, right? When I'm running something on my laptop, I very often don't necessarily know what configuration I'm using. I may think I know, but I probably forgot that I set this environment variable a certain way, right? When you're running on a cloud, everything is snapshotted in an image that you deploy, right? So that provides very efficient packaging and very easy to recreate packaging of your experimental environment, right? So for practical reproducibility, where you just want to run somebody's stuff, it's perfect. And it's something that you don't have to do anything special to do that, right? It just sort of happens by side effect of experimenting, by side effect of using clouds. So our users, I've got some numbers here, our users created thousands of digital artifacts that effectively describe their experiments. So testbed is a player for those environments. So what is now missing? Well, what is missing is several things. One thing is a packaging of your experiment that will be complete, right? So not just environment, but what you're running as well, right? And that will be integrated with your ideas and data analysis and things like that. Once you package your experiment, you somehow need to give somebody else access to that experiment and the testbed, right? Maybe they don't have a project, they can't access it otherwise. And you need some way for them to find those experiments. From the perspective of somebody who packages experiments, now they also want some packaging methods, but they now want different packaging methods than the person who's recreating, right? The person who's recreating places emphasis on how quickly they can, how easily they can recreate an experiment. The person who packages an experiment wants to be able to package them in a way that is cost effective, as quickly as possible, with as little hassle as possible, preferably as a side effect of what they're doing already. Then, yes, they would like to give access for reproducibility to others, right? We all would. And they need a place to share that work in progress. And so in Chameleon, we've got a solution for each of those concerns, right? They're reciprocal on the part of the person who packages and reproduces. So first, for packaging shareable experiments, I said literate programming. These days, the most popular implementation of Jupyter of literate programming is Jupyter, right? It combines ideas, process, and results in one nifty package, but it has one problem. Right? The coding cells in Jupyter, when you execute them, they run in Docker containers. Now, our users, they don't run their experiments in Docker containers, right? They run their experiments on something like this. Well, you've seen this before. It has all these switches and all these network circuits and all these nodes combined together for that experiment, right? So in order to now enhance Jupyter by a testbed, we integrated it with Chameleon. So when you write your Jupyter notebook, you log into our Jupyter server, your Chameleon credentials are implicit in those code cells so that from your Jupyter notebook, you can go out and you can create a repeatable Chameleon environment. And there's more stuff. There's always more stuff in some paper or other, and you've got references to that here. So that's for packaging. From the perspective of the developer of the experiment, they like doing Jupyter anyways, so that's a side effect of what they are doing. From the perspective of the user who reproduces them, that's very easy too, and has all these properties that I mentioned on the previous slide. How do people access this experiment? So we are back to that paper that I showed earlier, and in that paper it says, click here to reproduce. When you click, it takes you to this page. It takes you to a page where we store these experiments. And it says here, request DayPass, right? So a user can come to this experiment and request DayPass. When they click on that request DayPass, an email gets sent to the person who created the experiment. If they want to share it with that user, the user will get mail with a link. As soon as they click on the link, time starts ticking on their Chameleon access, right? So it takes 5 hours to reproduce the experiment. Let's say the author of the experiment gave them 8 hours. That's where it starts. And then finally, how do we share and find those experiments, right? So it seems to me that we need to rethink the familiar research sharing ecosystem, where we write papers, put them in proceedings, put them in libraries, and then there's an indexing system that finds them. Right now, when I read a paper, I don't really need anything else other than my eyes to interpret, and my mind, of course, to interpret what's in that paper, right? Not so with digital experiments, because they are zeros and ones. And we need some help to interpret those zeros and ones, right? In a sense, this is a very similar situation to what happens if you check out a microfilm from a library, right? So not a paper, not proceedings, but a microfilm. Library will give you access to microfilm reader, right? So Chameleon is such a place where you can get your digital experiment reader. And we originally thought, great. So there's this great digital publishing platform called Zenodo, created at CERN. Let's integrate with Zenodo such that our users can very quickly publish their experiments to Zenodo. They get digital object identifiers, can reference their experiments from their papers, problem solved. But it turned out there are users also want to use work in progress. They want to share work in progress. So for that, we created Trovi, which is kind of like a Google Drive for your experiment, right? You can put in it data, your Jupyter notebook, links to your image, what have you, anything that you need. And then you make it available, for example, via the DayPass, right? So we also give you a portal that where users can browse and filter and in general find those interesting experiments. It's integrated with Jupyter, with our Jupyter Access, so that packaging, when you develop stuff in Jupyter, you just with one click of a button, you can say publish to Trovi. And then you can also say, and now I'm ready to publish to Zenodo to make it shareable with everybody. Okay, so we're at the end of the talk, but a few parting thoughts, right? So first of all, science is constantly in motion, right? And scientific instruments need to adapt, right? So operating a scientific instrument is very much like laying the pavement as you walk on it to create your experiments. This is why we now took our cloud testbed and turned it into an edge-to-cloud testbed, right? Because our users increasingly wanted to run edge-to-cloud experiment. And something very interesting happened. The idea of a testbed underwent an inversion, right? Because originally conventionally, we think of testbeds as a pile of hardware, essentially. A lot of expensive provider-owned hardware, provider-operated hardware, a user come and check out this hardware. Now what happens, our users are telling us, we don't want hardware. Well, we want some hardware, but generally speaking, we don't want edge hardware, right? We have edge hardware and we have a lot of it because it's very inexpensive. And we want to operate it ourselves because we're going to put that edge hardware where we need to put it in order to work with our cameras, with our software-defined radios and other IoT devices. What we want from you is methods for sharing, sort of non-prescriptive sharing of those devices. And also we want a connection to a cloud and potentially to sophisticated networking capabilities and sharing methods and everything that goes with the testbed, right? So the idea of a testbed from something that gives you access to hardware evolves into something that allows you to share hardware, which is a different idea, right? So testbeds become places where you can get effective sharing and connecting to a residual resource in a testbed. And then last but not least, sharing your research digitally is very important. And I mentioned this workshop that we had with edge users last month, and that came through as a very important thing, right? Everybody wants to share. If the experiment can be packaged well, people are interested in what other people did. And just to give you an example, a very small example, last summer, so the summer a year ago, we had multiple students packaging various experiments, generally experiments with their own papers, but also some classic experiments like AlexNet paper, where the challenge was mostly, how to package an experiment in this environment and learn more about packaging. But anyhow, we ended up with many different packaged experiments. It turned out that one experiment, one of the newer experiments, was run by over 400 people 1 year later. That was an amazing result. Just imagine that you publish a paper and in the first year, it's referenced 400 times, right? So that just gives you an idea. There's an audience there for your digital experiments, right? People are really wanting to run them, to reproduce them, and it's a fantastic way to share. So to close, I want to invite all of you to come to Chameleon, share your experiments, interact with others, make it easier for all of us to work on science collectively. Okay, and I am done, and I will answer questions if there are any.
Thank you so much. Very fantastic introduction of this project. I was wondering, because maintaining all these hardwares even as a university is super complicated and maybe time consuming, cost a lot of resources. Have you think about uploading some of the hardware to public cloud, like Google, Amazon, and then, but of course, it might be complicated. Yeah, go ahead.
No, that's a very good question. And the answer is yes, we have. Not all of that can be, not all of the things that we do are done by the public clouds, by the commercial clouds, right? So the bare metal reconfigurability I was talking about, they don't provide that. The Amazon does provide it for some resources, but not for many. The virtualized resources can be accessed. And I said earlier, there's this NSF-funded project called Cloud Bank that provides access to, it provides access in funding and solves all the business, legal, and logistical barriers for researchers to use clouds, right? So they support that. And we've got a recipe for how to run experiments that use those commercial cloud resources and Chameleon resources as well, right? But you can use also just the commercial cloud resources using that, right? So that's this overcast paper that I referred to. If you go to our webpage, go to papers, it's one of the ones closer to the top. So that's all described there in more detail.